Hi everyone, today this tutorial deals with the double angle formulae which can be used in proving trig identities. So there are three main formulas to the double angle formulae. We have sine of A, sine of 2A. So double angle means that instead of just sine theta or sine A, there's a 2 in front of it. So it'll be sine 2A or sine 2 theta. So sine 2A is identical to 2 sine A cos A. Then cos of 2a, there are three equivalent identities that can be used for cos of 2a, which are cos of a, cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. And for proving any trig identity where we would have a cos 2a, it's only one of these we would need to use depending on what our aim is to get at the end, or what we are trying to prove. And then we have tan of 2a is identical to 2 tan a over 1 minus tan squared a. The double angle formulae are not given in the formula sheet for exams, so therefore you would need to learn these formulas. So example 1, prove the identity 1 minus cos 2 theta over 1 plus cos 2 theta is identical to tan squared theta. And if you look at the previous videos that we did, we can see the basic steps involved in proving a trig identity. So if you are not sure exactly how to go about it, you can always refer back to the previous videos that were done. It would be linked in the description below. So for this example, I'm starting off on the left hand side. So the first step would be to change the cos 2 theta using our double angle formula. Now we see that from the question, on the right hand side, we have a tan squared theta. We know that tan is identical to sine over cos. So that means that somehow we want to have sine terms in the numerator and cos terms in the denominator. And that is how we determine which of the equivalent identities we are going to use for the cos 2 theta. And in this particular example, we are using two different ones. So as explained, in tan squared theta, to get that on the right hand side, we need to work towards having terms with sine in the numerator and cos in the denominator, since tan squared will be sine squared over cos squared. So in the numerator, to replace the cos 2 theta, I want something in terms of sine. So if I look at the identities here on the right hand side, for cos 2a, the one that I have with sine is the third one. 1 minus 2 sine squared a, I'm going to use this one in the numerator. And if I want to have terms of cos in the denominator, for the cos 2 theta in the denominator, I'm going to use the second one, which is 2 cos squared a minus 1, where we just replace a by theta in this particular example. Alright, so this is just what I explained on why we chose these identities in particular. So the next step would be to simplify the brackets. So we have 1 minus, and it's important to have brackets. So minus 1 and minus by minus 2 sine squared theta will give plus 2 sine squared theta. And in the denominator, 1 plus 2 cos squared theta minus 1. I'm just rearranging the minus 1 here. So this will give us 1 minus 1 in the numerator, which is 0. So we will be left with 2 sine squared theta. In the denominator, 1 minus 1 here would also give 0. So we'll just be left with the 2 cos squared theta. And here we can see that the 2 can be cancelled from the numerator and the denominator to give sine squared theta over cos squared theta, which is identical to tan squared theta. And that's our right hand side, so we have proven our identity. Example 2, prove tan theta plus 1 over tan theta is identical to 2 over sine 2 theta. And again, with identities, we can choose to start either with the left hand side or the right hand side and simplify to get the other side. I have chosen to start with the left hand side. So we have tan theta plus 1 over tan theta. We can simplify our tan thetas to be sine over cos for each one of them using this identity. Tan theta is identical to sine theta over cos theta. Then our next step would be to simplify the second term, where I have 1 over a fraction that is equal to the reciprocal of the fraction. So 1 over sine theta over cos theta is equal to cos theta over sine theta. This first term remains the same. Next, I'm going to find the LCM and simplify. So the LCM of cos theta and sine theta would be sine theta cos theta, and cos theta into this would be sine, and then sine by sine will give us sine squared. Sine into our denominator will give us cos theta, and cos by cos will give us cos squared theta. And we know from the identities that we have learned previously that sine squared plus cos squared is equal to 1. So I can replace or simplify our numerator to give 1. So that is identical to 1 over sine theta cos theta. So if we look at what we would like to get on the right hand side, sine 2 theta from our identities is 2 sine theta cos theta. But what I have so far is just sine theta cos theta without the 2. So to get the 2, I'm multiplying by 2 over 2. So that means both the numerator and denominator is going to be multiplied by 2. Alright, now this is not going to change anything because 2 over 2 is equal to 1. And when we multiply anything by 1 it would be itself. So therefore, if I multiply by 2 over 2, it is just to simplify to get our result. So then multiplying the numerator by 2, I will have 2 there, and then multiplying the denominator by 2, it will give us 2 sine theta cos theta. Just to mention again, the reason why we chose to multiply by 2 is because on the right hand side of what we are trying to prove, we have a 2 in the numerator, and for sine 2 theta, looking at the identity, that's 2 sine theta cos theta. So 2 is missing from each numerator and denominator. So when we multiply by 2 over 2, we get the result that we want. And our denominator here is the same as sine 2 theta, that identity. So therefore, we have the right hand side of the identity, so it is proven. Example 3. Prove sine 2 theta over 1 minus sine squared theta is identical to 2 tan theta. So starting with the left hand side, I'm going to use the identity for sine 2 theta. From our identity here, we can see that sine 2 theta is identical to 2 sine A cos A, which would be 2 sine theta cos theta in this case. Our denominator remains the same for now. So if we look at our question, what we are trying to prove on the right hand side would be 2 tan theta. We know that tan theta is sine theta over cos theta, which means that I want terms with sine in the numerator and terms with cos in the denominator. So therefore, I am going to change the 1 minus sine squared theta using the identity that we have learned previously. Remember, we did that sine squared plus cos squared is equal to 1. And from that, we derive 2 other identities in which cos squared theta is equal to 1 minus sine squared theta. I'm using that identity. So 1 minus sine squared theta in the denominator gives cos squared theta. Right? And our next step would be to write cos squared theta as cos multiplied by cos. And then we can cancel these 2 terms, the cos theta and the cos theta. So we'll be left with 2 sine theta over cos theta. And we know that sine theta over cos theta is equal to tan theta. So that gives us 2 tan theta, which is the right hand side. So we have proven our identity. So I hope that you follow what we have done so far for double angle formula. Again, the process of proving identities takes a lot of practice. So it would be helpful to go back to the previous videos if you didn't understand what we did fully, to look at the tutorials done on proving basic trig identities. Then we moved on to the compound angle formulae, then the double angle formulae. So a lot of practice is required for understanding identities. So thank you for watching. An assignment will be posted sometime soon. So if you have any questions, feel free to contact me. Thank you.